Hello and welcome to this tutorial in which I will show you how you can run a sample size planning study for a confirmatory factor analysis in Mplus using a simulation. My name is Geiser. I'm an instructor with QuantFish. One question that I often get is, what is the required sample size for my CFA? How can I find out how much data I need so that my model will run properly and that I'll have enough power to show the effects of interest, for example, the correlations between my factors? And that question is more tricky to answer than it is for standard statistical methods such as a t-test or analysis of variance, where you can simply use G-Power or some other free power software that will tell you what the sample size needs to be given your expected effect size, level of alpha, level of power, and other parameters. With confirmatory factor analysis, it's more complicated since it's a multivariate method that involves latent variables, a model that has degrees of freedom, a model that can be incorrect, that can be tested using chi-square tests of model fit, a model that involves multiple parameters such as factor loadings, factor variances, factor covariances, error variances, and also for which it's also relevant to look at standard errors, convergence rates, improper solutions, and so on. So there are many more things to consider for a confirmatory factor analysis, and there's no simple G-Power software or button that will tell you, okay, you need 500 cases for this CFA. So one method that I usually recommend for sample size planning with CFA is Monte Carlo simulation, because that allows you to simulate an entire model under different sample size conditions, and then it gives you answers to a variety of questions about your factor model. For example, does the model converge at that sample size? Are the fit statistics reliable at that sample size? Are the parameters properly estimated? Are the standard errors properly estimated? Do you have enough statistical power? And other questions. And so, but then many people are scared and they don't know, how do I do a Monte Carlo simulation? That sounds complicated, and it's often something that is not taught in standard structural equation modeling courses at universities. So many people are lost and they don't know how to do it. Now, so I want to show you in this tutorial the basics of how to run a simulation for a confirmatory factor analysis for sample size planning using the Mplus software. Mplus is great for simulations because it makes it very easy, very user-friendly, and also the output is well organized so that you can see immediately pretty much whether your model works for a given sample size or not. So let's dive into it and let's look at this example output file here that I generated for this tutorial, where we will be looking at a two-factor CFA with two indicators per factor. And that's a prototypical example because in this scenario we have certain issues. One is that we have only two indicators per factor here, which is something that is not generally recommended, but sometimes unavoidable, because sometimes you just simply only have two indicators for your factor, and then you want to know, is this still something that's going to work given the sample size? Or what sample size do I need to make this work? Second, the indicators that I'm simulating here are not very reliable. And so reliability, or R squared, is something that matters for a CFA. When indicators are not so reliable, it means they do not have very high standardized loadings, and that is something that is detrimental potentially to a factor model, and that requires you potentially to have a larger sample size, as is the fact that we have only two indicators per factor, because it's been shown in more or in larger simulation studies, it's been shown that having more indicators per factor is beneficial as long as those are good indicators of the factors. So let's take a look at this. And so here you can see I have my 4 indicators listed in the Monte Carlo command in Mplus. This first of all tells Mplus what variables we are using here. We define the names of those variables. And then here I'm running a simulation with 50 cases. So a small sample to give us an extreme example of, does this work with a very small sample size, right? So that's going to be the sample size that will be examined here in this simulation right now. And then later on, I'll show you a larger sample size simulation as well. nreps specifies the number of replications that we use in our simulation, meaning the number of times that we draw from our population model that we're simulating. So we're going to draw 1,000 samples from the population model. You can think of that as being similar to a bootstrap. So here this would be a parametric bootstrap procedure where we are generating from a known population model, and then those samples, the model is fit to each of those Monte Carlo samples, and then we can determine the parameter estimates and standard errors and fit statistics for each replication, for each sample that is drawn. So the more the better, obviously, for higher precision, but 1,000 should be good. The seed value is sort of like the starting value for the simulation, and a good idea is to vary this random seed number a few times to make sure that that doesn't have a huge impact on the results of the simulation, meaning the simulation results shouldn't vary greatly for different seed values, and a good way to make sure that that's not the case is by running the simulation with different seed numbers that you could pick at random. Next is the specification of the population model. So here we set up our factor model or structural equation model or path model or whatever model we want to simulate in Mplus. And we're doing this by first of all specifying how each factor is measured. So F1 is measured by Y11 and Y21. And then the numbers that come here behind the star are the loadings. Now here I'm simulating a model for standardized variables because this makes it easier for me to set the loadings and set the factor correlation and also the error variances. And so the way this is done is by fixing the factor variances to 1 and then setting the loadings and the error variances in a way that they will be that the variables will have a population variance or model implied population variance of 1 also. So first step here is that the factor variances are fixed to 1, and that's useful anyway for identification. Otherwise we would have to fix a loading per factor, which we're not doing here. So here we're leaving the loadings free and we're fixing them so that they are in the metric of standardized loadings, meaning they can be interpreted as correlations between the variable and the factor. The first variable here has a loading of 0.7, meaning it correlates 0.7 with F1. And so that's not a terribly high reliability, or doesn't imply a terribly high reliability, because the reliability would be the loading squared, and 0.7 squared is 0.49, which is not a terribly high reliability value. In fact, it's pretty bad. So only 49% of the variance of Y11 would then be explained by the factor. So that's a pretty low reliability. The second variable has a standardized loading of 0.8 in my population model, which means it corresponds to a somewhat higher reliability of 0.8 squared equals 0.64. So 64% true score variance or factor variance. So that's a little bit better, but still not very good. And like I said at the beginning, I want to simulate something here right now that is not terribly reliable, because I know that that has a negative impact on sample size requirements. So I want to be sure that my sample size later on will be sufficient. So simulating something with pretty low reliabilities here is part of the game. The next one has a loading of 0.6, which is even worse. So 36%, or 0.6 squared is 0.36. So 36% explained variance is very low. And then again, I have one that's 0.7. Now, why can I interpret those as standardized loadings? Because A, I set my factor variances to 1, which means the factors are standardized, and also because I picked the error variances in a way that the squared loadings plus the error variance will add up to 1.0 for each variable. And that makes the loading standardized, because then also my observed variables are standardized in the model implied case, so that in the population they have model implied variances of 1.0. And so that's all I need to specify here. The loadings, the factor variances, the factor correlation, which I set to 0.5 here, and the error variances. The intercepts are not necessarily specified. Typically those are not of interest, and then Mplus just keeps them at 0, indicating that all variables are centered or mean centered with means of 0. Then you can copy your model population specification under model, and then that's the model that Mplus will then estimate in each of the samples that are drawn from the population. So we're fitting a correctly specified model here, which allows us to look at whether this works. So let's go down and take a look at the output. And so the first thing that we can see here is that input reading terminated normally, so there was no flaws. There were no flaws in our syntax here, which is good. We can also see that the number of observations in each of the Monte Carlo samples was 50, like we wanted. And then we can next, importance, we can see that not all of our requested replications converged. So only 922 out of 1000 actually did converge. So there was a relatively high percentage here of replications that did not converge, specifically 17.8%. 7.8% of replications did not converge. So that's a sign that the sample size is maybe not large enough. Now still we had 92.2% converged replication, so it's not that terrible, but still it's a sign that's not ideal. Ideally, all the requested 1000 replications should be completed. Next, we can scroll down and we can see the sample statistics for the first replication. So this allows us to check in a way that those values are not totally off or totally unexpected here. We get our means, which should be close to 0 because the variables are assumed to be centered. And then the correlations should be in such a way that we have two variables. The two variables that measure the same factor should be more highly correlated than the variables that measure different factors, and that's the case here. So you can see y11 and y21 are correlated 0.46, and then y12 and y22 are correlated 0.5. The other correlations are smaller, indicating that this is in line with the factor structure. Next is information about the model fit, and here in particular it is relevant to take a look at the chi-square distribution, or the distribution of the chi-square test of model fit. And so here we can compare the observed and expected percentiles and proportions, and so you can then see whether the chi-square distribution was reasonably approximated. When we look at the proportions here, we can see that that is not so much the case. It doesn't look so great. So the 0.05 region where we would reject the model when the p-value goes below 0.05, you can see that that is not super well approximated here. This would be 0.03, so it's somewhat not accurate. It's not horrible, but you can see that with a sample size of 50, maybe the asymptotic conditions of the chi-square distribution here were not quite met because the expected and observed proportions don't line up super well. So that could be a problem for chi-square model fit testing, because then your chi-square test of model fit may be inaccurate. Now let's go down and let's take a look at the other model results where we get the population value first. So those are the values that we specified, for example, here for the loadings. And then in the average estimate column, we see what the average parameter estimate was for the loading in question across the 922 replications that did converge. And so you can see that there was some bias here. So the average loading was 0.72, whereas in the population, the loading was 0.7. Now that's not too terrible, 0.72 versus 0.7, but for other parameters it was not as good. So for example, the second loading was 0.8 in the population and the average estimate was 0.86 about, so that was overestimated. Now other parameters are the correlation, which you can see here between the two factors, that was accurately estimated. So if all you're interested in is whether that correlation is adequately reproduced between the two factors, then that looks like it would work with a sample of size 50, as long as you have a converging model. So if you're only interested in that factor correlation, then there's no bias here in that estimation of that correlation, because 0.5 and 0.495 is very close. When we go down a little bit further, we see that we had especially though a problem with the estimation of the residual variances. You can see there's large bias in the estimation of the residual or error variances which do not line up between population and average estimate. There's quite a discrepancy here, and especially for the last variable y22 we have a huge problem because the average estimate actually was negative. So meaning the average estimate was a Haywood case, a grossly negative error variance that doesn't make any sense, negative 1.24, so that's terrible. And you can also see that this error variance had a terribly high standard error. So those are the next two columns. So the first one is the standard deviation of the parameter estimate across the 1000 replications, and then the next one is the standard error average across the 1000 replications, and those should also line up so that you wouldn't have any standard error bias. Now we can see here that even for the loadings, there's quite the standard error bias for all of the loadings, because there's a discrepancy here between the standard deviation of the parameter across replications and the estimated average standard error for all of those loadings. And that's typical. For small samples in SEM, we have a problem with standard error bias more than with parameter bias typically, and so that reflects what we typically find. And so this might be a reason alone to say 50 is not enough as a sample size, because if you have standard error bias, it means your tests of significance are also biased. And you can see that's also the case for the factor correlation, where the standard deviation was 0.21 about and the average standard error was 0.26, so that's too high. So this might cause you trouble with your test of significance for that factor correlation. But what I wanted to show you especially is how bad the standard errors were for the error variances. So A, those were all very high, and then B, they were extremely terribly high for the last variable here that caused a lot of Haywood cases, a lot of improper solutions, and so that shows you that really a sample size of 50 for this model is probably inadequate, at least from that perspective. And then another perspective is the coverage, the 95% coverage, where you would look at how many times the 95% confidence interval would cover the true parameter value if this confidence interval were calculated in those replications. And you can see here the coverage is pretty good. It should be 0.95, and so this is pretty close to 0.95 for those parameters. It's off a little bit more for the residual variances again, so coverage would be good. But again, if your standard errors as such are biased, then this may not be something that may be terribly important to you. Another issue is power, and that may be more relevant. So the power is showing us the percentage of, or is given by the percentage of times that a parameter was found to be significant at the 0.05 level across the 1000 replications, or in this case 922, which were convergent replications. And so you can see that power here was fairly low, so this should be 0.95, so should be the parameter that is non-zero in the population should be found to be significant 95% of the time. And here, so say the power was lower than that, 0.836, which may still be okay, but then for other parameters it was lower. For example, for the factor correlation, the power was only 0.6, so only in 60% of the replications did we find that this correlation was significant at the 0.05 level, and that's not okay for a correlation of 0.5, which is a strong correlation. So that is low power. Again, that's due to the small sample size. So in summary, we can see that the fit statistics didn't work super well for a sample size of size 50 for this model, and also bias was found at least for some of the parameter values, the error variances. Standard error bias was found here. Power was inadequate for at least some of the parameters, so the conclusion here would be a sample size of size 50 is too small for this model. Let me show you now an example where we have a larger sample for the same model. So I simulated this model again for a sample size of 250. So now when I go back up to the input, you can see that now the n observations was changed to 250. All other commands were the same. So it's the exact same model specification, but now simulated for 250 observations in each replication. So when we go down, we can see that now all 1000 requested replications were completed by Mplus. So we had we had no problems actually with convergence anymore for this sample size. That's a good sign. And when we scroll down to our fit statistics, to the chi-square, then we can see that also the chi-square distribution was more reasonably approximated. When we look at the lower end here, we can see that those expected and observed proportions correspond well to one another now. So using the chi-square distribution to find the p-value for the test of model fit would now be appropriate and would work well with the sample size. So this is sufficiently large for a good chi-square approximation for this specific model here. Furthermore, we can see when we go down to the model results that now we have much less bias here in both the parameter estimates and also the standard error. So you can see that there's hardly any discrepancy now between the population value and the average estimate, and there's also hardly any discrepancy now between the standard deviation of the parameter across replications and the theoretical standard error estimate or average. So that's good because it shows us that we neither have parameter bias nor standard error bias here. We can check that as well for our error variances, and you can see even the error variances now are pretty close. They still have a little bit more bias, and that's because the indicators are not so reliable and because we have only 2 indicators per factor, which is suboptimal. So there's more bias here, but it's still relatively negligible. You probably wouldn't care about whether your error variance is 0.64 or 0.63. It doesn't really matter. So not a lot of bias. The standard errors are also really good looking now for the error variances. There's not an improper solution here anymore, as far as we can tell, at least from the average estimate. So that looks better. And then also we can now take a look again at our coverage, which looks really good. It's close to 0.95 for all parameter estimates, and the power is much improved. So you can see here that now the power for the factor loadings is close to 1.0, if not 1.0. So here for those 2 loadings, they were found to be significant in all 1000 replications. And also the power to find significance of the first 2 loadings was also very high, as was the power for the factor correlation, which you may care about more than the test of significance for the factor loading. So power was highly adequate with a sample size of 250. Now, one more thing that we should look at in the output is the Tech9 output at the very end here, which tells us whether there were any improper solutions. And you can see that there were still quite a few instances here. So you can see error messages for each replication, if any. So if there were any improper solutions, then that message would be printed. And so you can see there was one in replication number 23, one in replication number 39, 50, and so on. So there were quite a few improper solutions still, meaning solutions where there was one or more negative error variance for an indicator. And that could be problematic as well. So this could be a reason to use an even larger sample size. If you feel like I don't want to run into this problem of an improper solution, then that's sample size dependent in this case because the model was correctly specified. So we know that this problem must be due to the sample size. So in that case, you may try, for example, a sample size of 300, 350 to see if then you find fewer replications or maybe 0 replications that will return an improper solution. I hope you found this video useful as a crash course to how a simulation study can be used to determine the adequate sample size for a confirmatory factor analysis. Check out the description for additional resources, including courses that I teach for QuantFish, and I'll see you next time.